Dear students, today we will study a very interesting topic, but it's impossible to tell you everything or even something, uh, something overwhelming about all heterocyclic compounds. This is a very broad field of knowledge, so my task to tell you about only some heterocyclic compounds, some chosen heterocycles which are important because of their biological roles. So, sorry about a systematic way. My target is to show you how heterocyclic compounds are incorporated and in the biomolecules and how they afford their biological activity. A few words about classification. They can be classified in different ways, but first of all, they are cyclic compounds which contain one or more atom different from carbon. So generally, it can be not only nitrogen, oxygen, and sulfur, it can be phosphorus, even americium. But I never saw even in scientific papers and scientific articles the examples of heterocycles with americium. We will see mostly about common heterocycles with nitrogen, oxygen, and sometimes with sulfur. Just they are very important. I said you that this is a very broad topic. They can be found in alkaloids, nucleotides, vitamins, flavonoids, and you can see here that here we see the heterocycle from aglycone part, yes, and but sugar also consists, yes, cyclic heterocycle. So cardiac glycosides, because of sugar fragment, is also heterocyclic, and in cardiac glycoside we have a heterocycle in steroid fragment. Antibiotics and some amino acids. By the way, biosynthetically alkaloids and antibiotics in many cases they derived from amino acids. When saying about synthetic pharmaceutical drugs, just I can propose you a lot of structures. Some of them, neuroleptics, barbiturates, antihistaminic drugs, antibacterials, anti-tumor, and so on and so on and so on. So heterocycles are very important, but the topic is very broad. So only chosen very important, biologically important heterocycles. Few words about classification. Very simple. It depends, first of all, on the size of cycle. 3-membered, 4, 5-membered, and so on. Just, it's not difficult. 3-membered, for example, oxygen containing, 3-membered, nitrogen containing, 4-membered heterocycles, yes. Just names given this page are optional, not mandatory. And 5 and 6-membered heterocycles, which are very important for our course. You need to memorize all the historic names of these heterocycles: furan, pyrrole, tetrahydrofuran, pyran, pyridine, pyrimidine, and 1/7-membered heterocycles. I advise you to memorize it because azepines are basic structures for a lot of neuroleptics. The second approach to classification is a type of heteroatom: oxygen, sulfur, or nitrogen. So it will be nitrogen, sulfur, oxygen containing. If you will meet phosphorus, it will be phosphorus containing. And now we can join two classifications: 5-membered oxygen containing heterocycles, 5-membered nitrogen containing heterocycles. And again, you can see heterocycles can be with 1 or with 2 or with 3 or with more atoms. Also, we can classify according to aromaticity: aromatic, non-aromatic. I said you about number of heteroatoms, yes, 1, 2, 3, sometimes 4. And we can say about some fused heterocycles. Fused cycles contain 2 general atoms for 2 cycles. So indole and purine are fused heterocycles, and pyrimidine is monocyclic heterocycle. Hoping it's not difficult. As for nomenclature, Common historic names are possible, absolutely systematic. We will omit this chapter, it's rather difficult. And some systematic names based on heterocycles, historic names. So these historic names have been included by EU PAC into the system of substitutive nomenclature. Just when saying about systematic nomenclature, there is some ranking of priority for nitrogen, sulfur, and oxygen, and also for hydrogenated and free of hydrogen, nitrogen. Yes, this is some very general approach to systematic nomenclature. So this is optional. You can see, yes, the names are formed from some roots which are typical according to the name of the heteroatom and the size of cycle, and on the level of saturation of heterocycles. Yes, some examples, it's not very difficult. You see that, for example, for 7th member heterocycles we have epene. So yes, as epene. Perhydroazepine, it means without double bonds. Triazole, thiodiazole. Again, repeating once more, this material is optional if you will be interested. Especially, you will be able to stop the presentation and to start this nomenclature. But you are obliged, you are required to know historic names which have been incorporated in general systematic approach of the substitutive nomenclature of EUPAC. Please memorize all these names. This is mandatory for N-pyrrole, terpene, and indole. In all these heterocycles, numbering will start from heteroatom. Yes, nomenclature will be based on common names, but then we will apply general approaches to systematic nomenclature. For example, 2-nitropfuran. We started from oxygen, and we weren't left because in such a case we obtain for nitro group the lowest possible number. But the first number is attached to, yes, belongs to oxygen because in monocyclic heterocycles heteroatom has the priority. Yes, sometimes for monosubstituted derivatives, alpha beta nomenclature is also applied. So, alternative name alpha nitrofuran. How to name this aldehyde? Because aldehyde group does not belong to the parent structure. In such a case, instead of al suffix, yes, we apply carb aldehyde suffix, and as a result we obtain furan 2-carb aldehyde structure or historic name for furan. Yes, a very important amino acid, proteinogenic amino acid. This is tryptophan. When we have chosen the name based on amino acid parent structure, yes, it's typical because we are discussing proteinogenic amino acid. This heterocyclic fragment we will name indolil, and we need to show to determine the place where a heterocycle joining the parent structure, so beta indolil. Or we can say also indol 1, 2, 3, 3-il, it's also possible. And now I remind you how to determine the stereochemistry. Yes, when ranking substituent we obtain amino group has the highest priority, then carboxylic group, and finally indolil methyl group. Hydrogen behind the plane, everything is okay, so rotation, yes, rotation for substituents except the youngest, the hydrogen, yes, amino the first, then the second. We are rotating, we obtain S configuration counterclockwise. Or we can apply the biochemical name L-tryptophan. We will study all these historic names for proteinogenic amino acids in a lecture devoted to proteinogenic amino acids. Few words about aromaticity. Just I remind you some general approaches. First of all, we need to find cyclic conjugation and to number electrons in this conjugation. I remind you that the full information is available in lecture devoted to chemical bond. Yes, you can see that in pyrrole and in thiophene we have 1, 2, 3, 4, 5, 6 conjugated electrons, and 6 corresponds to Hückelrück. For sure the system is plane, all atoms in sp2 hybridization. In indole we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Again, it corresponds to Hückelrück. Yes, so all these systems are aromatic. Please, please, I want to remind you that pyrrole is not basic on nitrogen. We can say about acidic NH side, very weak acid, but still acidic, but not basic, and a very slight basic side, mostly we can say about nucleophility of pyrrolic ring. Yes, and when interacting with very strong bases, we can obtain the corresponding anions. This material again is optional. Whether oxygen or nitrogen is able to add hydrogen? Yes, but in such a case we will lose aromaticity. So it has no sense to say about the basicity of nitrogen. When we will add hydrogen plus, yes, we will lose aromaticity. So pyrrole is not basic, but when interacting with hydrogen, we will obtain the destruction of aromatic structure, and such substances we name acidophobic. After the reactions with acids, this term was broadened to interaction with oxidizers, when heterocycles also lose their aromaticity. So nowadays the term is applied both for acidic and oxidizing agents. Furan is extremely acidophobic, and when we apply regular reagents, we are losing its aromaticity, and because of further polymerization, we obtain resin. Yes, just saying in simple words, instead of normal regular reaction, we'll obtain some mud. Thiophene is rather stable to action of acids and oxidizers. I said to you that pyrrolic acidity is very weak, so only the action of extremely strong bases will afford us anions. This material again is optional. Few words about electrophilic substitution in these heterocycles. We said, I reminded you that fluorine and pyrrole are highly acidophobic. They're afraid of acids and oxidizers, so they are required some special mild reagents for reactivity. So for nitration, no nitric acid. This is a mixed anhydride from acetic acid and nitric acid. Yes, in such a case, in such a reaction, we obtain nitrofuran. Sulfonation can be done with pyridine sulfide, yes, instead of concentrated sulfuric acid. Bromination for furan is possible only with a complex of furan and bromine. This reaction is optional, but please keep in mind that interaction of furan with pure bromine is not possible. It's possible, but we will obtain some mud, not the more normal product. I said to you that thiophene is rather stable, so just regular reagents can be applied to obtain chlorides, sulfonic acids, and acetyl derivatives. Oxidation will give us the product with lost aromaticity, but some regularly will obtain some resins. And now I want to show you a very interesting substance, porphine. Formally, it contains pyrrolic systems, but we need to say about some general aromatic systems with 18 electrons. It's not possible to say about some separate pyrrolic rings. Yes, we have a general system, and this structure is very important in bioorganic chemistry because substituted porphine, protoporphyrin, is the fragment of hemoglobin. Hem is prosthetic group of this protein. When oxidized, porphine is destroyed to give bilirubin, orange pigment, and it can be determined by chemical analysis, just the manifestation of some diseases. Indole, in other words, benzopyrrole. Yes, I said to you that this is aromatic heterocycles with 10 conjugated electrons. It contains benzene and pyrrole ring. Properties are very analogical to pyrrole. First of all, it's non-basic, it's very important. Again, the same approaches, mild reagents, giving us substitution products. This material is optional. Some biologically active indole derivatives. First of all, tryptophan we discussed. When oxidized, we obtain hydroxytryptophan, which is after decarboxylation give us serotonin. We will discuss this further in topic about amino acids, but now I will say to you that products we obtain after decarboxylation of proteinogenic amino acid we name biogenic amines. Biogenic amines they play different roles, but all of them play the role of neurotransmitters. Serotonin, a very important chemical messenger, yes, and it's associated with the feeling of happiness we obtain from different activities. Some other important biological transformation of tryptophan will give us indole-free acetic acid. This substance is very important for plant chemistry. Synthetic indole derivative indomethacin is widely used in pharmaceutical chemistry. It's widely used in medicine as non-steroidal anti-inflammatory drugs. Please memorize this abbreviation and say it. Yes, again, non-steroidal anti-inflammatory drug. Proline is proteinogenic amino acid, and nicotine is an alkaloid. Few words about six-membered heterocycles. You need to memorize pyridine, quinoline, and isoquinoline. Yes, and I pay your attention that in isoquinoline numbering starts from non-heteroatom fragment, yes, from carbon atom. And we omit these angular carbons. If we need to describe them somehow, it will be 4A, yes, 8A, 4A. And oxygen containing heterocycles pyran, depending on the position of hydrogenation, we can say about sorry, here a mistake here, 2H here for H pyrans, and pyrrolium cation, which is aromatic. Pyridine 3-carboxylic or nicotinic acid is an important vitamin-like substance and also a fragment of nicotine, amide, adenine dinucleotide. Uh, pyridoxine, pyridoxal with aldehyde group, and other derivatives. They are different forms of vitamin B6. Quinolinones and benzopyrrole derivatives have a lot of biological activities, and flavone is the basic structure for flavonoids. Yes, here we see flavonoid parent structure with the fragment of sugar. Sugar fragment are glucose fragment. Uh, Rutin is the example of flavonoids. This material is optional. Few words about aromaticity of pyridine. In contrary to pyrrole, we don't need the electron pair from nitrogen to obtain aromaticity. We have pi conjugation. So nitrogen has its own lone electron pair. So it's basic. This electron pair can take part in acid-base reactions and also in reaction with nitrogen as nucleophile. Yes, this is pyridine type of nitrogen. It's basic. Yes, again, all atoms in sp2 hybridization, flat structure, cyclic conjugation, and 1, 2, 3, 4, 5, 6, 6 conjugated electrons, pi conjugation, and finally lone electron pair. But because of the action of nitrogen, pyridine is pi-poor system. Pyrrolium cation is also aromatic, so unexpectedly this cation is rather stable, and it can be found in nature in different flavonoids. Repeating once more, pyridine is a weak base. Still, some salts are possible, and I remind you that NAD plus, NAD H, NAD P plus, NAD PH, all they contain nicotine amide fragment. Yes, this is the basic structure when NAD plus abstracts hydrogen minus from hydroxy or sometimes amino containing substrates. Hydrogen plus also eliminates from the structure. As a result, we obtain NADH, yes, hydrogenated, reduced NAD, and oxidized form of substrate. Hydrogen plus will be abstracted with the enzyme, yes, the abbreviated form. In physiology, in many cases, instead of two hydrogen plus and hydrogen minus, scientists apply such a notation, but in real this is the same. Two electrons plus hydrogen plus, we will obtain hydrogen minus. Yes, so this is the same. Yes, the reaction is applied to lactic acid. As a result, we obtain pyruvic acid. Just again about different forms of vitamin B6, pyridoxal aldehyde group, pyridoxal, pyridoxal amine phosphate. So it's very pyridoxal phosphate. It's very easy to identify the necessary structures: pyridoxal, pyridoxal phosphate, pyridoxal, pyridoxamine, and pyridoxamine phosphate. I remind you that vitamin B6 participates in different decarboxylation of amino acid and in some transamination reactions. Some heterocycles with two and more heteroatoms. We start with pyrimidine. We have two basic centers again. Conjugation from 3 pi bonds, pi give us aromatic system, and so nitrogen, both nitrogens, they have lone electron pairs, so both nitrogens are basic. Pyrimidine bases are parent structures for nucleic bases, and that is why for nucleosides and nucleotides we will study this topic in special lecture a little bit later. Just only a few words. With two hydroxy groups, dihydroxypyrimidine, yes, but this form can be converted easily in the solution to the oxo form. Cyclic amides are lactams, and the corresponding hydroxy derivatives is lactam. Just we can say about dynamic equilibrium between two forms. Just these forms are interconversed because of the transfer of hydrogen from oxygen to nitrogen and vice versa from hydrogen to oxygen, and just the shift of the double bond from nitrogen carbon to carbon oxygen fragment. Isomers which are interconversed in the dynamic equilibrium we name tautomeric forms. So we can say about tautomeric equilibrium, about the phenomenon of tautomerism, lactam tautomerism. Yes, examples of pyrimidine nucleic bases. In nucleic acids, they are present mostly in lactam form, but in some pharmaceutical drugs, lactam form is also possible. But again, as for nucleic bases, we will study them specially in a lecture about nucleic acid. Yes, one more pyrimidine nucleic base is cytosine. Just again, lactam tautomerism possible, but here we can say about amine-imine tautomeric equilibrium. Yes, here we see the transfer of hydrogen from amino nitrogen to heterocyclic nitrogen and vice versa, and again the shift of the double bond. Pyrimidine is also the part of some biologically active substances such as vitamin B1, its common name thiamine, vitamin B1, and you see that it contains both pyrimidine and thiazole heterocyclic fragments. Yes, hoping you will be able to analyze the structure of this vitamin, pyrimidine and thiazole. Thiamine takes part in biochemical process in activated diphosphate form. Just when you will be asked about the functional groups, you can say this is amino group. Yes, this is esteric fragment, and this fragment is anhydride from two fragments from phosphoric acid. Thiamine is crucially important in decarboxylation reactions of alpha oxo acids. Barbituric acid is a synthetic substance. Just you can see here the fragment of urea. Yes. Just a few types of tautomerism is possible for barbituric acid. Just this acid is very important that two substituted derivatives of barbituric acid are applied as barbiturate pharmaceutical drugs, sedative and hypnotic drugs. For example, this substance is phenobarbital. Yes, lactam tautomerism is possible for barbituric acid and its barbiturate derivatives. Yes, and for pure barbituric acid is also cational tautomerism is possible. Yes, the transfer of this hydrogen. But I pay your attention that all barbiturates, I'm saying about pharmaceutical drugs, they contain two substituents in this position. So for pharmaceutical drugs barbiturates, cational tautomerism is not possible. Yes, for pure unsubstituted barbituric acid it's possible. Imidazole, the heterocycle, 5-membered heterocycle with two nitrogens. One of them is basic pyridine type, and the second is acidic pyroyl type. Because of amphoteric properties, imidazole is involved in the transfer of proton in acid-base catalysis. It's very important in enzyme chemistry when imidazole containing side chains of amino acids take part in transfer of hydrogen. Yes, hydrogen jumping from amino acid to substrate to coenzyme and again to amino acid of protein. And imidazole is part of a lot of biologically important substances. We said previously that indole is a fragment of tryptophan. Just we can find it's also in some medications. For example, some anti-inflammatory and antidepressant substances. Some indole-containing substances found in fungi possess psychiatric activity. Purine-based heterocycles can be found in purine nuclease base, for example, adenine, again amine tautomerism, and fuguanine, lactam, and amino-amine tautomerism is possible. Just for these bases, the formation of hydrogen bonds is very typical, and this is the principal reason for complementarity of nucleic bases. It's very important for functionality of nucleic acid. Again, we will discuss this problem in topic about nucleic acids. Degradation of purine bases will give us some modified substances, hypoxanthine derivatives, and finally we will obtain the metabolite of purine nucleic bases, purine heterocyclic bases, to uric acid. Uric acid, this is the substance that can be presented in the form of hydroxy containing compound, and 2-hydroxy group will have acidic properties. Uric acid forms 2 series of salts, and depending on the number of ionized hydroxy group, it will be more or less soluble in water. So monosodium urate is soluble in water, and disodium urate is almost insoluble in water, and this salt can be precipitated in some organs. In junctions, it causes very strong pain, and it also destroys the function of some inner organs, for example, kidneys. The excessive production and reservation of uric acid is connected with the disease, metabolic disorder, GOAT. It can be regulated with some medications, and some dietary helps people to transform disodium salts in more soluble monourates, which are dissolved in water and can be excreted from the organism. Just some substances, they inhibits xanthine oxidase inhibitor. Such substances are allopurinol, and it's applied to treat GOAT. Nicotine is alkaloid. It was found in tobacco, and you know that it interacts with special nicotinic receptors. Just this is a reason for tobacco addiction. I said to you previously that all alkaloids are biosynthesized from amino acids. Just here you see the optional scheme of indole alkaloid biosynthesis. Again, I remind you that nicotine-3 carboxylic acid, nicotinic acid, can be obtained synthetically from nicotine, but there is no metabolic connection with nicotinic acid and the nicotine. It was obtained simply synthetically approximately 200 years ago. And nicotinamide is an extremely important substance because it transfers in vivo a hydride anion in a lot of biochemical processes. Alkaloid caffeine is purine based and it's present in coffee. Some other heterocyclics are pairing structures for some alkaloids. And in general, alkaloids are heterocyclic compounds with basic properties. In next lecture, we will discuss briefly the occurrence of alkaloids in nature and their application in pharmacy. Thank you for your attention.